In this video, I would like to talk about some aspects of nervous system physiology and what goes on in the membrane of neurons. So the first topic is the concentrations of the important ions, sodium and potassium. They're both positively charged, but they have opposite gradients. And so that's something we talk about in class. But what I want to talk about is how those gradients are maintained. How is sodium maintained at a 10 times higher concentration outside the cell than inside? And how is potassium at a much more than 10 times greater inside than outside? So there are three reasons. And one of them is that there is always a negative charge inside the cell pulling positive ions towards the inside and pushing negative ions towards the outside. Now again, we have to keep in mind that every ion has its own gradient and just gets pushed because of that, but also it gets pushed by the overall charge imbalance, so the electrostatic attraction, either to the inside or outside. So there's always those two forces acting on any ion. So one of them, regardless of where all the other ions are, inside or outside, regardless of whether the membrane is polarized or depolarized, there will still be anions inside the cell. And so they're always contributing to that overall balance. Also, potassium is always crossing the membrane. In whichever direction it is being pushed, it's able to cross better than sodium can. So sodium is usually stuck wherever it is unless a channel opens for it, but potassium can move better than sodium can. So potassium is going to tend to leak across the membrane. And finally, the pump, the sodium-potassium pump that pumps sodium out and potassium in, is always going. It's not fast enough to oppose an action potential or a graded potential, but it is fast enough to pretty quickly get back to the resting potential afterwards. And it has to constantly go to maintain those imbalances. So those are the forces that maintain the concentration gradients. So there's another topic that looks at this in a different direction, and that is, what can we learn from the Nernst equation? The Nernst equation lets us compare ionic-related phenomenon as they would theoretically happen to as they would happen in the presence of a gradient. So what would happen without the gradient versus what would happen with the gradient? That's kind of what the Nernst equation lets us look at. And we use it in a very specific way in this situation, where we're looking for the equilibrium potential. So that's going to be a number in millivolts. And remember, negative 70 millivolts is the resting membrane potential. And it might be good to pause the video and tell me, what is the threshold potential? The threshold potential, again, is minus 55, roughly, millivolts. So some millivolt value is what we will get. And what we're going to do is, for any ion, so we'll start with potassium, we'll think of what is its concentration in the extracellular fluid at equilibrium, what is its concentration in the intracellular fluid, how many charges does potassium have, and that's 1. So it's going to be 61 times the logarithm of potassium's extracellular versus intracellular concentration. And so this is going to give us basically the offsetting force that would dissuade an ion diffusing. So here's what it would look like if we plug the numbers in for potassium, and what we would get would be negative 90 millivolts. And that means that at negative 91 millivolts, potassium would not move out anymore. Because remember, if you open a potassium channel, the resting potential, potassium is going to flow out. That is despite the fact that potassium has a positive charge and there's an overall negative charge inside the cell. Potassium's concentration gradient can push it out harder than the overall electrostatic forces at -70 can keep it in. But if the overall membrane potential was -91, then potassium's concentration gradient could no longer push potassium out of the cell in any large amounts. A better way of looking at it would be potassium could move in and out at equal rates if the potential was -91. And I think you'll remember at hyperpolarization, a membrane can't reach -91. So what if we do this for sodium? So again, potassium is going to flow out of the cell unless the membrane potential gets down to around -90. What about for sodium? So for sodium, we do a similar calculation, and we find that its ion gradient is reversed, so we get a positive number, and we get a positive 1 for that. And so for sodium, the membrane potential that would hold sodium still would be +60. So sodium its gradient is pushing it into the cell so strongly that you would need an incredibly depolarized membrane to stop it. And we never see that level of depolarization. +60 is a higher, more positive than what we get at the peak of an action potential. So sodium, what this tells me is that sodium will always be pushed into the cell under any physiological condition, and we need the ATPase pump to push it back against those forces that push it into the cell. Okay? So potassium, if we go back to potassium is going to tend to move out of the cell unless the membrane potential gets down to a very low level, very hyperpolarized. So these two ions oppose each other. Sodium is going to tend to move in, and potassium is going to tend to move out. So that's what we can learn from the Nernst equation. Okay, so something we looked at in lecture was what happens at a synapse. And we didn't look at this level of detail, but we're going to do that shortly. What we thought about at a synapse was that vesicles full of neurotransmitters would fuse with the membrane and release the neurotransmitters, and receptors would bind to those neurotransmitters, and the receptor would see that as a signal, and it would open some kind of ion channel. That's usually what will happen. So that's what's going to happen at a typical synapse. Neurotransmitters will cross the synapse, receptors will detect them, and then do something as a result of that. In the case of the nervous system, we're usually thinking of opening ion channels. Now, I want you to tell me, let's review real quick, which ion channel or channels would be excitatory, which would be likely to push a neuron towards an action potential. So go ahead and pause the video. Tell me which kinds would be, which kind or kinds would be excitatory. So I hope what you said was sodium. If a sodium channel opens, sodium will rush into the cell, and it will depolarize the cell and push it from the resting membrane potential down at -70 up to -55. That's when an action potential could be triggered at the axon hillock. So generally, sodium channels will be excitatory. Potassium and chloride channels will be inhibitory. And we'll come back to this in the next video.